movie came out, Should I Sell My Shore House? And for those of you who don't know, in Jersey, we don't go to the beach, we go to the shore. You got a problem with that? He's a Rutgers guy too, by the way. He sits next to me in the football games. To study sea level, you can look at it on different time scales. The most precise is satellite altimetry, which is really related to, relegated to 1993 to present. Tide gauge data go through the 20th century. You can go stick a core down the beach, as a lot of us have done. You look at the Holocene transgression, go a little further back. Reef terraces are good at least to 130,000, maybe a little further back. Oxygen isotopes do provide a proxy for sea level change, but they are an equation and two unknowns, both sea level and global compositional changes in seawater due to ice, and also temperature. And that's been the holy grail of paleoceanography to solve that. I do sequence stratigraphy and this method. Sequence stratigraphy is looking back upwards of 1 billion years. I'm only taking this back 100 million years.
Captain, incoming message.
Sorry about that. I didn't know I had mail. It didn't work before. I forgot to quit out of it. Yes, that's Mr. Worf. So, the second half of this talk is the stuff I really do, which is deep time, as John McPhee dubbed it. And the first half is stuff that you can chat with Al Gore.
If Greenland broke up and melted, or if half of Greenland and half of West Antarctica broke up and melted, this is what would happen to the sea level in Florida. This is what would happen to San Francisco Bay. A lot of people live in these areas. Here's Manhattan. This is the World Trade Center Memorial Site. And after the horrible events of 9/11, we said never again. But this is what would happen to Manhattan. They can measure this precisely, just as the scientists could predict precisely how much water would breach the levees in New Orleans. The area where the World Trade Center Memorial is to be located would be underwater.
So if Greenland broke up and melted, this is what would happen. And Al Gore is illustrating a 5-meter rise, 15 feet. It's a screenshot from the movie. When this came out, I started getting those phone calls, and it brought up some interesting questions. By the way, this clip is very powerful. I've shown this at 28 different universities and a ton of citizen groups and stuff. And in fact, on this audience, it's no different. Most of you have seen it before, but it's still a very powerful clip in the movie. And of course, Al Gore was castigated for this by the English court, and Judge Burton ruled this as one of the 9 deadly sins of Al Gore's movie, and the most cardinal of which was the sea level story. Well, how long will it take to achieve Gore's 5-meter rise? By the way, I've had given this in a couple citizens groups where I called it a Gorean world, or a Gore world, and people came back very offended. I voted for the guy twice. I mean, I would have voted for him twice. But it is a political issue. But the point is that we know the geological record has done this in fairly recent past. This is Greenland during the Eemian, about 125,000 years ago. Marine isotope Kron stage 5e. About half of Greenland had melted, and about half of West Antarctica had melted. But what was the time scale for this change? And that's one of the critical questions. This is from the IPCC, which I assume everyone knows what that means, Intergovernmental Panel on Climate Change, the 2004 assessment report. This is model years for Greenland for projection into the future. I've scaled this into actual calendar years, so we're looking at, well, let's do it this way. This is Captain James Tiberius Kirk. He sailed in the year 2266. He wouldn't have to worry about this happening. Neither was Jean-Luc Picard, who sailed in the year 2364. In fact, to actually get, according to the IPCC anyway, you'd have to go. Bruce and I are probably the only two to remember this song. Okay. This is often painted as the global warming controversy. And there is, it seems like a controversy. Time magazine, the cute polar bears, and Gore's movie. And Jim Hansen said this in the New York Times. He gave us a Gore view that Greenland melting will put New York City underwater. I don't know if you have a PERG here, public students, good organization, but they take things a little far. Jersey Shore is going to disappear in 100 years, a quote to my son's class 2 years ago. Michael Crichton, State of Fear, and of course many of you know Richard Lindzen, who basically put a couple of very strong letters into the Wall Street Journal about the climate of fear. And I'm personally involved in this because, by the way, this is Waretown, New Jersey, and that is my shore house. So we're on the front lines of yeah, I know. Not in my lifetime, though. That's the take-home. He's getting ahead of me. You all know about the Keeling curve. I don't sound like Al Gore, and you know it well. Okay, Charles David Keeling first measuring CO2 at the top of Mauna Loa in 1958, and the familiar pattern of going from a pre-anthropogenic level, which was down here at 280, as we know from ice cores, that's in parts per million, right? To, well, today we're at 287, and it's going up at 2 parts per million per year. What this does is an increase in concentrations. Trying to predict the future is difficult, but certainly the scenarios that we're looking at are going to lead to an atmospheric doubling by the year 2100, unless we do something really dramatic. Even in the case of near shutdown of current emissions, we're still going to higher emission levels. This is the prediction of temperature. And it's been criticized by a lot of people in the blogs. This is the IPCC estimate. It's done on models. I'll come back to that in a few minutes. But basically, the question is, I like to pose these questions, is the warming going to be 1.5 degrees, or is the warming going to be 4.5 degrees? And for 30 years, the answer to that question is yes. Okay? 2.5 is maybe the best guess, but that's the error. This is showing the 20th century warming from instrument scale records. This is NOAA. You could take this from Hadley. You could take this from GISS. They're all about the same. This is CO2 over the same period. This is very prominent in Michael Crichton's book about what happened in the 1940s. I'm not a climate scientist, I'm a paleoceanographer, so I got sandbagged on this question. I said, oh, what happened? Well, here's CO2 and the warming since the 1960s, and the two behave in lockstep, which is good because it's as predicted. One of the reasons why this cooling or lack of warming, is really, I would call it, it's not cooling, occurred, has been dubbed due to global dimming, which is in part of the solution. The sulfate aerosols suppress the warming to the greenhouse gases. But also, in order to fully understand it, it's this climate, it's complex. Broccoli's models at Rutgers, I think I best speak to this, is saying that you need to combine both volcanic aerosols, lower solar input in this period, and sulfate aerosols into the solution. And this, to give you a perspective, is the tide gauge data from Atlantic City, New Jersey. And I take my perspective on this problem is both Jersey-centric, okay, but it's also sea level-centric. I will look at climate change through sea level colored glasses. One thing is, just because CO2 correlates with temperature doesn't mean there's causality. This is a famous cartoon on the effect that the number of pirates has gone basically down at the same time as global warming, and so of course they're obviously not related. By the way, the good news is number of piracy is on the rise, so that means we're going to global cooling, right? And I always said I could take my sea level curve or oxygen isotope curve, this is my oxygen isotope curve, and scale it to stock market quotations. And they're beautifully correlated here, okay? Of course, I don't have the crash on here, by the way. But here's a fact to take home, actually. CO2 will double in the century, almost certainly. Without feedbacks, doubling of CO2 increases global heat by about 4 watts per meter squared. In the absence of feedbacks, the Charney report in 1979 says we will see at least a degree of 1.1 degrees of temperature rise. The Charney report in 79, without using global climate models, predicted that the doubling of CO2 would result in a sensitivity of climate temperature of between 1.5 and 4.5. If you look at the model outputs, that's our uncertainty still. So we are heading for warming. That will result in a rise in sea level. Now, how much? The 2001 IPCC provided an estimate of 40 centimeters with an error from 20 to 80. Much ballyhoo about the 2007 report, they reduced the upper limb. They still had a best estimate of 40 centimeters, but their upper limit was on the order of 60 and their lower limit was on the order of 20. They did not include Greenland melting. They only included, as we'll see, the so-called steric or temperature effects and alpine ice sheet melting in this. There's definitely an underestimate, and I'll show you that. So what is the data? The 20th century tide gauge data. Now we close out the 20th century, we can say a fair degree of certainty went up about 1.8 millimeters per year, or about 0.6 of a foot. Okay. In 2008, the best estimate from satellite data for the period from 1993 to 2006 was published, and it had more than almost doubled. It was up to 3.3 millimeters per year, or a foot every century. It's Topex and Poseidon data which is used. It's a group, Annie Cazenave and others have used this data to measure. The advantage of satellite data, as I'll show you in a couple of minutes, is it's much less noisy than, said, tide gauge data. Why is the sea level rising today? The thermal expansion effect explains from the 20th century the oceans have warmed about 0.6. That would explain about half of the signal. The other half is from alpine glaciers. Obviously, melting the Arctic ice sheet doesn't really affect sea level, but melting of ice sheets. This is a Mulan in Greenland from the cover of Science from Roger Brathwaite. We do know alpine ice sheets are on a major recession in most ice sheets. Yes, Michael Crichton's book is correct. There are a few that are expanding due to precipitation effects. One of the other deadly, parenthetical here, one of the other deadly sins of Al Gore is that the snows of Kilimanjaro are supposedly disappearing, not due to global warming, but due to reduced precipitation. But Lonnie Thompson would argue strongly against that and say that snows in Kilimanjaro are disappearing due to global warming. But the disappearing of these lovely alpine ice sheets and ruining my favorite skiing places gives us only about 0.6 of a millimeter per year. The other part is coming from probably Greenland. With the original IPCC report, they had Greenland near zero. The 2000, that would be the third assessment report. The 2007 report didn't take anything into account because the new data were just coming out that Greenland is now contributing about 0.6 of a millimeter per year. And so I'd say, when I started this lecture series about 3 years ago, I said, well, we're going to see 40 centimeters. It's 1.2 feet. When I saw my shore house for 1.2 feet, no. Okay. And then Stefan Ramsdorf published this in Science the same week that the fourth assessment IPCC report came out. This is showing the tide gauge data in the background. This is showing the satellite data in blue. You can see it's the same data sets in here virtually. The tide gauge has more noise in it. This is the IPCC best estimate, which intersects 2100 at 40 centimeters. This is the IPCC worst case scenario of 80 centimeters. Empirically, we can say that we are tracking at the 80 centimeter. We will see a minimum of 80 centimeters. Now, there was, if you follow the blogs, there was a paper from Cazenave that updated from GRACE data now. The first ones were from Topex and Poseidon, but from GRACE data, that going up to 2008, that the sea level rise was a little bit lower. So Stefan just emailed this to me last week, where he's now plugged in the new data, and basically it falls just slightly below the line. So where is sea level going to be in the future? Well, prediction is very difficult if it involves the future, as Neil Bohr says. I've did various fits to the data sets, and if you take the 1970 to 2007 data sets, they're very Ramsdorfian 90 centimeters. But here's the warning. This is where the geological record becomes important. This was the rate to the same scale during meltwater pulse 1A during the last deglaciation, which is 33 millimeters plus or minus 10 centimeters. Excuse me. All right. We also have to worry about subsidence.
And you know, I'm just curious, you know that from what data?
Which one?
The
I will go there.
Oh, okay.
I will show you the meltwater pulse 1A data in a minute. I'll derive that. New Orleans is not threatened so much by global sea level rise, okay, although one can analogize it, tell that to a guy that's up to his nose in the ocean, that sea level is going to rise this much more. 10 millimeters per year of subsidence in New Orleans, and then Bangladesh. Okay, so subsidence can be very important. Here, was it about a millimeter per year in North Carolina, as it is in New Jersey. I like this figure from Norb Sudi because it illustrates the processes that we look at when we look at the geological record. For the 20th century tide gauge data, sea level was rising, if you remember, about 2, right? regional subsidence is modeled by Dept from the unloading, basically what they call GIA, glacial isostatic adjustment due to Laurentine unloading, is a millimeter per year. So if you go to the Battery in New York or Lewis, Delaware, you see 3 millimeters per year in this region in the 20th century. Atlantic City and Sandy Hook have higher local subsidence, and they get about 4 millimeters per year. Sandy Hook is a sand spit, it's prograding into Sandy Hook Bay, and it's compacting. And Atlantic City is like Venice. I said that once, and Kevin Burke said, Atlantic City is nothing like Venice. Well, they're both subsiding extra because of groundwater withdrawal. Okay. And if anybody's interested, we can talk about that later. So now let's begin to look at the geological record. Rick Fairbanks gave us where sea level was 18,000 years ago. Until 1989, we didn't know where sea level was in the last glacial maximum with a factor of 2. Was it at 80 meters or was it at 150 meters below present? And the answer was yes. Rick showed that sea level was 120 meters below present and rose in the famous French two-step. These are dates on Acropora palmata, fossil sunshine, if you like. I'll blow that up for you. Okay. In order to get the younger part of the record, though, Rick had to splice in records from the Caribbean, basically, and Florida. We did some work here. This is New Jersey. This is Barnegat Inlet. And we did some work along these beaches that addressed this younger ages, the younger part of the curve. So this is Acropora palmata, fossil sunshine that he dated. So the rates in meltwater pulse 1A were on the order of, in the original Fairbanks, minimum 20 millimeters per year. With new dates, they may be as high as 40 millimeters per year. The errors in between the truth shall lie. So that's where I got it from before, Emily. That number comes right from that curve. But the problem is, though, so we knew it rose 20 meters in this less than 1,000 years and another 20 meters here, and it slows down. What happens over the past 5,000 years? Well, this is where some of our New Jersey cores became very useful. It certainly has slowed down, but one of the debate is the planet was so deformed by the ice sheet that much of the southern hemisphere is experiencing uplift, and you'll read about the mid-Holocene high stand to sea level. We don't think that that's true at all. The IPCC and others just assume the sea level change over the past 5,000 years has been flat, 0. I don't think that's true either. Looking at our data sets in New Jersey, we took a bunch of different cores from SUDI and our own ones that we took. A bunch of radiocarbon dates that we evaluated and evaluated various indices and the reliability of there. And just fit a linear regression through. We get a rate of about 1.8 millimeters per year over the past 5,000 years. But we know substance from modeling by Peltier and Lambeck comes out at a millimeter per year, which predicts about a global change of about 0.8 millimeters per year over the past 5,000 years. The Caribbean reefs that Rick Fairbanks looked at, he actually took them Leidy's data, that's showing here. They show about 1.26 millimeters per year. Lambeck's modeled about a half of a millimeter per year of substance for those locations. So we would conclude that the natural global sea level rise over the past 5,000 years, this doesn't include any millennial scale, submillennial scale variations. This is just over the past 5,000 years, sea level has generally risen at about 3/4 of a millimeter per year. So this is kind of like the Al Gore plot where he goes on the cherry picker and shows how we go off the charts. This was the natural background variability that we just derived. This is showing us picking up the 20th century and the tide gauge data, and now we're seeing it going up and up and up. We are off the charts from the rate of rise. We can safely, one of the things that a skeptic will always say is, but this is part of a natural cycle. Well, this is not part of a natural cycle at all. If you look at it from sea level colored glasses, we can say that unequivocally. That's the Holy Veil. It was actually the Holy Grail. Anybody who's taken a geology course has heard of Peter Vail, of Exxon Production Research Company, and the sea level curve he put out in 1977, and the subsequent ad hoc hypothesis from Hock, Hardenbowl, and Vail that came out in Science. So this is the going back through the Jurassic. This is the Cenozoic. Just for reference, this is mid-Oligocene sea level fall, and their curve is 160 meters. Well, that's greatly exaggerated, and the take-home on this is we've spent 20 years dating these similar sequences in New Jersey and elsewhere, and say that most of the timing of these events on these curves is correct. But the amplitudes, to quote one of my co-authors, Nick Christie Blick, are meaningless. Sequences are unconformity bounded units in their simplest form. This is a sequence boundary in Outcrop in New Jersey. We have a shore face sand here, a basically low stand systems track, erosional deposit, and then in fairly deep water, say 50, 60 meters paleo depth, transgressive systems track. So our approach has been to date these and drill these and date them. This is the region of we've been working in. We started out collecting these Ewing seismic data. I'll show you this profile in a minute. And while we were driving the Ewing up here in 1990, I looked on shore and said, boy, we're going to drill these sites out here with the Jordy's resolution, we thought. It'd be a lot cheaper to drill on shore. So we've now completed our 13th onshore site, actually 14, including we drilled down in the Chesapeake Bay crater, and we're able to use these to put together our first round sea level curve. We're actually now, 20 years later, going to complete drilling these 3 sites, and I'll come back at the end of the talk. If you've never seen the Exxon method, I can teach you a coastal on-lap in 2 seconds. This is a seismic profile going from near offshore all the way to the continental shelf slope break. This is 1 second two-way travel times, about 1 kilometer. We're looking at these lower Miocene prograding packages building outward. This progressive up-dip termination is on-lap. We don't know if it's coastal or not. Progressive down-dip termination is down-lap. There's an erosional truncation. This is called top-lap. These are seismic sequences as recognized using the Vail method. By the way, Vail received the Franklin Medal a year and a half or 2 ago, and he always gets the debate about Vail is he gave us the sea level curve that some people don't like. What he did give us, which is unequivocal, is a new way to look at the stratigraphic record in terms of these sequences. So we went to drill and date these. We drilled onshore at Island Beach at first in 93, and here at Cape May, 94. This doesn't look like what you think of the Jersey beaches. It's quite pretty, like your beaches here in North Carolina. This is exactly what you think the Jersey beaches look like. That's the Trump Castle Hotel and Casino, okay? Bruce, that's New Jersey to you, right? And of course, this is our beloved JR, which sails tomorrow on its inaugural expedition after its extreme makeover. And she drilled in New Jersey. I work on cores. We collected about 20,000 feet of these cores, these different locations. And it's a 2.5-inch diameter view of the world. But even with a 2.5-inch diameter view of the world, you can see these unconformities or sequence boundaries. We date these things with either fossils or strontium isotope correlations. This one's basically between the Eocene and the Oligocene. We've dated 14 of these in the Miocene, 8 of these in the Oligocene, 12 in the Eocene, 7 in the Paleocene, and 15 to 17 in the late Cretaceous. These packages are very useful. These unconformity bounded sequences give us a prediction. Generally, the pattern we see is deepening across the sequence boundary. So we go from a shallow water sand, as I showed you, to a deeper water glauconite. We've cut out the low stands for the most part. So we are getting a clipped record. We have a transgressive systems track when sea levels beginning to rise, a maximum flooding surface, and then this regressive package as we go from pro-delta clay silts to quartz sands of delta front. The reason why the state of New Jersey gave us a ton of money to do this, in addition to NSF and ODP, is because these sands are our aquifer units in the coastal plain. And we give a prediction from our sequence stratigraphy as to their continuity and predictability. This is what the data looks like. This is an example from the lower Miocene. Our logging units are feet. I'm sorry, we're barbarians. We don't use meters in the field because that's what the drillers give us. These have these erosional boundaries. We identify the cores. We see these, we date these with strontium isotopes in the Miocene typically. They're basically transgressive, regressive, transgressive, regressive, transgressive, regressive. These are water depth curves, in this case put together using benthic foraminifera and lithofacies reconstructions. Caveat right here, our greatest uncertainties in the method I'm eventually using to reconstruct Eustace in New Jersey, which is almost an oxymoron, is from the water depth interpretations. We're able to take these same sequences out to the continental slope, take them out here, and we drilled and dated them on the continental slope on ODP leg 150. And we're able to show you this interim result for the Oligocene into the Miocene. So there's about 24 million, 23 some million. This is the geomagnetic polarity timescale. What's shown here is blue are the times represented by sediments onshore. By compositing a bunch of these records, we're able to say this is a local sequence called the Kirkwood Zero. The white is a time gap. The time gaps here line up with those seismic sequences, what we date on the slope, which makes sense. There are time gaps associated with them. So they line up, which suggests that these are regional base level lowerings. And they line up very well, surprising. They also line up with oxygen isotopic increases. If we look at the global oxygen isotopic record for this interval, this is the famed MI event. I named it. It's not named for Miller 1. It's named for Miocene isotope 1. Okay? And it's about a per mil increase in benthic foraminifera. And so the question is, how much of that's ice volume and how much of that's temperature? And the answer is yes. Probably about half this is ice. But the point is the inflections in these oxygen isotopic increases uniformly line up perfectly, almost perfectly, with the hiatuses, which means the hiatuses when sequence boundaries were cut during a glaciostatic lowering. Makes sense. Got it in science 10 years ago. But we kind of knew that the ice sheet, large ice sheets began in the Oligocene. So that's kind of like a no kidding, Ken. The secret then is to get sea level. Well, you have to account for all these effects. You have to decompact your sediments. Okay? You have to unload them. We assume generally airy loading, ice cubes in a glass. Okay? This equation is called the backstripping equation, and was written by Tony Watts initially to reconstruct tectonic substance. Tectonic substance is equivalent to, this is a flexural parameter, which is 1 in case of airy, so you don't have to ignore it. This is the decompacted sediment loading, sediment thickness. This is the loading parameter for that sediment in an airy world. This is the change in sea level. This is the loading effect at that sea level. Water depths are observable. And the way this equation is written, it's an equation with two unknowns, that if you know tectonics, you can compute sea level. Tectonics meaning assuming simple thermal substance. This is showing the kind of data that we generate. What's shown here is the best estimate, the error bar. Michelle Comans is very careful to make sure we prescribe what our error bars are. Some of them are quite large, some of them are quite tight. This is for one site called Ancora. This is another site called Bass River. So this has been decompacted and unloaded. She then fits a best fit empirical thermal substance curve to it, which actually predicts how much stretching occurred. And the difference between the best fit and the data is called her R2, or her residual 2. And what the residual is a eustatic estimate or any non-thermal tectonic components. We've done this at a bunch of sites in Jersey and Delaware. We get very similar results. We compare some of the results to backstripping in the Russian platform. I'll show you in a few minutes. We think in general, New Jersey is actually, other than my practice, my home state, is actually a very good place to study sea level because there's very few tectonic overprints. Probably not zero. You can't just do sea level in New Jersey. So this is a first round curve that we put together. Bill Van Sickles did his master's thesis with Michelle Comans at Western Michigan. We had 6 sites here in the Miocene. He was able to put these together for a first order sea level curve in his paper. Problem was we had Cretaceous, we only had 2 sites. One of them was fairly deep water, Bass River. They didn't totally agree. The problem was there was no other sea level curve to use. When people would ask me, what should I use for sea level? I'd say, you can't use the hot curve because it's for example, in the middle Oligocene, 2-dimensional backstripping by Comans and Carr suggests a big mid-Oligocene event of Vail that they have is 160 meters. It's real, but it's about 55 meters. And even the relative amplitudes weren't correct. Okay, so what are you going to use? I said, well, I kept calling Michelle and said, we need to find a way to average these data or put them together. She says, you really want to do this? I said, yeah, I think we should. Well,
Choirs, a mean, futile, and stupid gesture be done on somebody's part. We're just the guys to do it.
so we did it. There's a story behind this. One of the reasons to show these movies is wake you up every about 20 minutes, right? I had Lloyd Kegman, Woods Hole, sound asleep until that movie came on. Okay. So we did it, and we modestly call these the new Miller curves. I'll show you this. It was published in Science in a paper called The Phanerozoic Record of Sea Level Change. We submitted these curves initially for the past 100 million years, And Jesse Smith was the editor. They sent it to Hawk, they sent it to other people to review, and they all liked the paper, and they recommended it. And then Jesse came back and said, I want to see this paper, I want to see that paper. And about a week later, he called me up, we're going to reject it. And I go, why? He goes, well, this part Van Sickle published, and isn't this your 1987 auction isotope curve? And I go, yes, but Jesse, we never put it together with the Cretaceous curve. It was a new Cretaceous curve for the auction isotopes, which are in red here. The blue are sea level curve. The black are our low stands, which I'll describe in a minute. I said we never synthesized it in this manner. He said, what? He goes, synthesize. I'll get back to you. So he called me back about 2 days later. Be careful what you ask for in the world. He called me back and said, well, we're going to accept the paper as a synthesis. But we just don't want you to do the last 100 million years. We want you to do the whole Phanerozoic, that is 543 million years. And we want it in 2 weeks. So what this is, by the way, is, I'll point out, we generally don't capture the low stands. In a few places we do. We get the full amplitude of sea level. For example, in this one, Michelle used what Jim Browning dubbed the WAG method for the low stands. That is wild-ass guess. Only constrained by the fact it's not falling any more than the previous one. Okay. But the point is, the scale of these in the Cretaceous is 15 to 25 meters. The scale in the Oligocene, where we have a more complete record, is on the order of 55 meters. In the Miocene, Michelle called me up and said, why is the Miocene less than Cretaceous? I said, because we clip the low strands really badly in the Miocene. And we scaled the auction isotopic record, something Rick Fairbanks is telling me to do for 25 years for the youngest part, because we run out of marine section in New Jersey as sea level fell too far to capture anything but occasional high stands. And we redid this in 2008. One of the problems was we knew our Cretaceous underestimated the peak of sea level. We only had sea levels at 70 meters above present. And I taught a generation of students from Walter Pittman's Gospel that sea level in the mid-Cretaceous was 250 meters. Well, Michelle went back and redid this with a bunch of new sites. We have many more Cretaceous sites that were added in, and a couple of years later. And color is her curve, very similar to ours, but we've improved it a bit. And the peak in the Cretaceous is reached at about a little over 100 meters, about 110 meters. Okay. This just shows all the sites that now, each of these is a time interval represented. As Derek Ager said, there's more gap than record. You know, we've been drilling and compositing these things, and for the past 100 million years, we have about 66 million years represented in the core. That means we're missing about 34 million. And as far as this is a sea level curve, I think old Winnie said it best about democracy, that it's been said ours is the worst form of sea level curve except all the others that have been tried. This is a model to test against other places. Now, the long-term component. Walter Pittman, for years, from reconstructions of seafloor spreading, had sea level at about 250 to 320 meters above present. Reconstructing seafloor and spreading rates. A lot of it is constrained by the fact that the Cretaceous quiet zone had very high, apparently high spreading rates. But also, you're trying to reconstruct something that's 50% not there. Older than 50 million years, half the ocean crust has been subducted. So David Rowley has said the null hypothesis is there's been no changes in seafloor spreading rate. Every geochemical model you look at, every CO2 model you look at in the past 100 million years is implicitly tied to this pulse of high seafloor spreading rate. So this is not a trivial problem. It's a very important problem. I don't want to sound like I have the answer here. Ours is much lower, but the implications are interesting. So Comans went out to prove her professor wrong in 1984 and wrote the most interesting paper on this subject I've ever written. But she came out with 230, which is what Exxon used. I will show you in a minute. But her error analysis showed Rowley was almost correct. It could have been 45 meters. What do you want it to be? Okay. Stackler and Watts did the first backstripping paper, studied the ocean margin in offshore New Jersey, and their backstrip estimate for the peak is 120 meters above present. When I gave this at lunch 2 years ago, Mike stood up and said, you know, I never knew why we got it wrong. I said, Mike, you may not have gotten it wrong. You just had your office down the hall from Walter, and you were listening to Walter. The two estimates are independent of these, are one from Chris Harrison, who measured what's called continental freeboards, but how much of the continents are flooded. And what Chris did is looked at every continent. Now, we know Africa sits high today. We know that Australia was high and sits low today. North America, we assume it hasn't moved. We love North America, right? But it probably sat low in the Cretaceous, okay? So what Chris did was just average them all together. They got 150. Gerard Bond came through and did the Russian judge, like in skating, right? You throw out the high, you throw out the low, and you average the rest. And he came out with 135 meters. So we conclude that the best estimate's on the order of 150 plus or minus 50. It's often cited Exxon used 250. I got this from Exxon last week, and it just showed what they did was they basically used Pittman's envelope, and they hung the long-term curve right on of their curve. They took Pittman's curve and scaled their curve to Pittman. And that was the original Vail curve. And in 1987, they scaled it to Komen's. Okay. Dietmar Muller just published a paper in Science, okay, and this is where it actually gets really interesting. So we published this paper, and we have these fairly low amplitudes. Everybody assumed it was 250. And 3 papers came out in a row in early 2008 saying, well, Miller's wrong because New Jersey's affected by the subducting Farallon plate, and so it sat basically high, and so you're not getting as high an estimate. Muller's estimate for reconstructing ocean floor is this dotted line here, and it's at about 170 for its peak. But again, look at the error bars. They're huge. It could be 50, it could be 250. This is the Haw curve. This is the Haw curve envelope, and this is our estimate for long term. Okay, so Michelle tried to scale ours to his and say, okay, this is the uplift in New Jersey, and maybe they are correct. Maybe New Jersey did set unusually high due to this effect. One of these papers, it was Mucha et al. In the APSL, had a great title. There's no such thing as a stable continent. Our reference frame, when I take home from this, is I've looked at sea level on a lot of different scales. The ones we know the least about are the very longest scales, because you don't have a reference frame, stable reference frame. The continents do move. And the other one's the very shortest scale, where we have this glacial isostatic deformation of the planet. I think we're starting to center in on understanding the sea level changes and the in-between scale, particularly Milankovitch and others. So, over the Oligocene and younger, we have large variable Antarctic ice sheets, and they control the sea level change. That's not shocking. From the late Pliocene to recent, from about 2.6 million, we had very large northern hemisphere ice sheets. It's first demonstrated by Sir Nicholas Shackleton. 2.6, the northern hemisphere ice sheets were large, the sea level changes were large. We do have these changes, which are large and rapid, in the Cretaceous. And the only way to do these large, rapid sea level changes is by the growth and decay of ice sheets. Yet we have assumed that the world was ice-free, and this is what, let's see, you guys would be at the beach right now, okay, in an ice-free world. But there's obviously evidence that the poles were quite warm. You can't have alligators next to ice sheets. But this is our hypothesis, and it has been very warmly received that there were ice sheets in this greenhouse world. And this reminds me to give a little history. It's especially, I think, important for students. We all think we discovered something. Matthews first suggested that, from the isotopic record, that there were ice sheets in the Eocene. Of course, his style was, prove me wrong, okay? Dan Schrag and Heller Stoll came, and everybody ignored him. Ted Mortimer once stood up and said, Bob, sit down and shut up. You know there were no ice sheets before the Middle Miocene. Okay, we know there are ice sheets now that go back, certainly to the Oligocene, that were very large. Stoll and Schrag tried to push it into Cretaceous. We did the same. Recent paper in Science provides some very good data for this in the Cretaceous. It wasn't until I read this paper by DeCanto and Pollard, which shows these series of maps, that I began to understand how you could put an ice sheet ephemerally on Antarctica. These are models that are done for Eocene configurations, applicable in principle to the older record. This is what a 15-meter sea level fall would look like. This is what a 25-meter sea level fall would look like. These 3 nodes here, the Transantarctic Mountains, Drawning Maudland, and Marie Birdland, I think it is. No, it's Gambutsa Plateau and Drawning Maudland. These 3 loci would give you a fairly significant ice sheet, yet left most of the coastlines completely outside the influence of ice. We know that by the earliest Oligocene, we had a big ice sheet. We had ice calving off and ice raft of detritus extending further north than it does today. And that would have been about a 50 to 80 meter sea level fall associated with, say, this event here. So this kind of gave us a feeling for what the million-year scale variability would look like. And this model from Dave Pollard and Rob DeCanto illustrates the Milankovitch scale. This is the heartbeat of the development of the ice sheet across the Eocene-Oligocene boundary. Only in the Oligocene, when ice filled the continent, was due to the fact that CO2 fell below about 3 times present. A little uncertainty, I think, in that. Rob would say 2.80. But this basically is what it looked like in the Oligocene. Begin to wrap up the last couple of slides. Coming back to, we compared our backstrip record with a backstrip record from the Russian platform, and the interval of overlap, they're actually remarkably similar. This is some Dork Sahagian's work. And it extends back and shows that the long-term variability on the order of 100 to 150 meters and the short-term million-year scale variability on the order of 15 to 20 meters is replete throughout this section. In the older section, it's much less certain. We all know that the Cambrian was almost a water world. There was very high sea levels. But whereas the long-term sea level was at 200 meters above present, as backstripping by Marge Levy and Michelle Comans would say, or was it lesser, like on the order of 50 meters, as Bond's work would say. And I don't think we know, and this is a fertile area for study. But it contrasts dramatically with 3 generations of exon curves. The original Vail in green, the Hawk curve in 1987 in purple, and this gray one was Hawk's 2005 curve. Again, their timing of their events is correct, but their amplitudes were wrong. Future work. Well, getting at these actual amplitudes is a thorny problem. ODP put a whole leg on the Northeast Australia margin. They drilled fossil sunshine here. They drilled out in the basin. They backstripped it, and the first answer that came out for an 11 million year event, shown right here, was about 85 meters. Gary Carter set his poster up next to mine at AGU. So why does Ken only have 40 meters in New Jersey? Well, we've clipped the low stands, okay? So they went back and redid it, and they got 33. Well, how did they get 33 meters? Isn't that different than 85? I would think so. In this case, they assumed this was a completely rigid plate, completely rigid. In this case, to get 33, they assumed complete area isostasy. Just shows you that the assumptions can muck up your results. Cedric John submitted this to geology. I had pleasure reviewing this good paper. I said, guys, you got to go back and model this and the rigidity, what you think your best estimate is. And they came out with about 55 meters, which I think is probably pretty good. And that just shows that New Jersey, we clipped these low stands. But we're going to get them if Lucy doesn't pull the football out again. And 2006, 2007, 2008, we suited up for this big dance. The big dance is to go out here and drill sites MAT 1, 2, and 3 in a focused experiment to get amplitudes of sea level change for these Miocene sequences. These are lower Miocene sequences. This is the Oligocene right here. This is the middle Miocene here. And we're drilling at these 3 sites as part of the Integrated Ocean Drilling Program, Expedition 313. Greg Mountain's co-chief. I'm just going out for fun. And we're going to use a platform like this. This is the WAN. It is a lift boat. It jacks itself out of the water. It's self-propelled, so it's a boat, not a barge or a jack-up rig. It's like a jack-up rig, though. Cantilever. This is in recovery operations. Greg Mountain took this picture for Katrina. We couldn't get it in 2006 because it was doing recovery operations, and then it sank the following year. Okay, and went to the bottom. Nobody injured. Nobody got hurt, but it wasn't available. Last year there were contractual problems. This year we're good to go. We were planning to be out there. So that's why Greg put this together. It's like Lucy pulling the football out. We keep getting ready to kick it and it goes away.
So there's sort of temporary rigs that can go from place to place?
Yeah. The problem with it is these are slow. They are self-propelled, but they have to hug the coast. They're very slow. It has to be mobilized out of Louisiana. It'll take it 2 weeks to get up to New Jersey. We're paying for that mobilization. Total cost on this is about $11 million. DOSEC will act as the primary subcontractor to. The money comes from the Integrated Ocean Drilling Program through the European Science Foundation to the European Science Operator, ESO, who then contracts, if you ever had anything to do with the drilling program, it's a bunch of alphabet soup. But it's the British Geological Survey is the European Science Operator. They have contracted with DOSEC. And DOSEC is contracted with Monco to get the boat. We're using a DOSEC drilling rig, and we're using a DOSEC crew.
And the Dept is what?
The depth is 30 meters of water depth at all three sites, more or less, and target depths are 800 meters. One of the issues is logging while drilling is an expensive tool. They didn't budget for that. Greg is logging while drilling, and we may lose one of the holes instead. That's the trade-off. That's how the program works. A fixed budget and under contract. But it looks like we're going to go. Then we spend November in Bremen having a party with all 25 members of the science party in Bremen working up these cores. So the conclusions. On the long scale, 10 to the 7th years, this is probably one of the most interesting, actually. There's no such thing as a stable continent, but long-term sea level fell by about 150 meters. This is consistent with smaller changes in spreading rate than have been conventionally assumed by most people. On the million-year scale and Milankovitch scale, we think that there were ephemeral Antarctic ice sheets. The Bornemann paper measured oxygen isotopes and had a period of very high oxygen isotopes in the mid-Turonian for about 200,000 years. So that's what we mean ephemeral. Each of these cycles is about 1.5 million years or so. They're not quite periodic, as we can determine. So for a period of only 2/15 that you were in this mode of a small ice sheet. Big ice sheets didn't, the icehouse world still began in the Oligocene. That's the take-home message for people. You didn't know that. That's been the byline of paleoceanography since we were the first people to say it. The icehouse began at 33.8 million to be precise. And the northern hemisphere ice ages make that 2.6 with the new time scale. On the more human time scale, sea level's been rising over the past 5,000 years. 20th century is about 1.8 millimeter per year. And today, well, take your money, pay your choice, somewhere between 2.5 and 3.3. And so the final slide is, well, quick story behind this. I gave this as GSA to a climate skeptics group. And it was really kind of an ugly situation. Half the people in the audience were very much against this group, and the other half were very much for it. And I presented this last slide. And someone nailed me after the talk and said, this is a little too glib. I say, don't sell insure. From the perspective of owning a mortgage, the first thing when Lauren or I will say when somebody calls me up, they'll say, well, where is your house? Should you sell it? And there's a lot of places you shouldn't know, maybe mine. The bays are very vulnerable to flooding during storms. I can show you a picture of my house underwater, or the basement underwater. What we will see is at least 80 centimeters by 2100. New Jersey will see at least 100 centimeters, as will you, as you add in subsidence. Best guess globally is that it will be over a meter. Probably not going to be 2 meters, but it's certainly going to be more than 80 centimeters. More beach, well, Warren should get up and give this part, the final part. More beach erosion, more cost to replenish, loss of marshland like my house. Increased storm intensity is a question mark. It really is. Even Kerry Emanuel has written showing that there seems to be an increase. It's backed off a little bit about that, but it's a good question. But I'll leave you with this thought. In answer to the person who said, you're a little too glib, this is a glib answer. Don't you care about your grandkids? Yeah, my grandkids are moving to my shore house. That's for sure. And when we first published our curve, they did a satellite NPR, and the middle segment was on us for about 20 minutes, and the last segment was on the Dutch about engineering and the IPCC. But the first segment interviews some scientists from Vanuatu, former New Hebrides, which is shown here. One of the other deadly sins of Al Gore was that there was supposed to be no evacuations due to climate. There's no climate refugees, Al, according to Judge Burton. Well, actually, there was. And Tiga Island was evacuated in Vanuatu. And Tuvalu and Carteret Island's been evacuated. Tuvalu is very threatened. These islands will disappear, okay, in the next century. And I just want to let the last word be heard from the person from Vanuatu. If I get that going.
That's the only thing that I would like to say for all those who are listening, that think of those that are coming behind your children or your future generations.
Lothar Mapat and Brian Phillips speaking to us from Vanuatu in the South Pacific. In a moment, we'll move stateside to hear from Rutgers University geologist Ken Miller.
Yeah, you already heard from him. Thank you.
So what had he said? We missed the beginning of it. What did he
His English isn't really good. He basically said, well, what I like to say is, I would say to you, think of those who are coming behind. That's all he said. And that was the point. And your children and your children's children. So the glib answer is from my mortgage, I'm not worrying about this. I'm insuring, okay? And unless it's in a highly threatened area. And that's the answer for a citizen who's really worried about making his mortgage payment and whether or not he should be having this house there or not.
On an island.
You're not going to
True.
sell. You're not going to sell because there's no market.
that's happened in the past 6 months. But yeah.
But my understanding is that they, Australia and other Pacific Rim continents are trying to put together, basically evacuate these islands and patriotize them or whatever onto the mainland.
They are.
Yeah.
And it depends on the extent. I mean, you will read, the blogs are actually good to see both sides. I always like to say I like to stay in the middle of a controversy and fire at both sides, okay, because they're both end members in this case. But there are claims out there from, remember, Nick Moner, okay, Crazy Nick, saying that none of these islands are threatened, that sea level is actually falling on these islands because these islands are in a part of particularly where the oceanography is one of the dominant effects on the tide gauges. So during El Nino years, there's a 10 or 20 centimeter switch in where sea level is doing. So he takes the tide gauges selectively and shows that they're falling. These islands are threatened and will be, with a meter rise, many of them will begin to disappear.
Well, let's thank Ken.